Hello organic students. Today in lab we're going to be looking at the stereochemistry in the Diels-Alder reaction. Here I've shown you the reaction to make cyclohexene, but you need to remember two things you need for the Diels-Alder reaction, and that is a diene and a dienophile. In this example our diene is 1,3-butadiene and our dienophile is ethene. Now if we push arrows we can clearly see how we're able to get our cyclohexene product. Otto Diels and Kurt Alder won the Nobel Prize for this reaction in 1950, and today, 70 years later, it's still a relevant method, and that's mostly in part due to the fact that Diels-Alder is an example of a pericyclic reaction, which is a very powerful method to make six-membered and bicyclic rings, which is important to the fields of pharmaceuticals, to natural product synthesis. They're just very useful reactions, and there are three main types. The first is a sigmatropic reaction. This should be familiar from your organic lectures because two examples of a sigmatropic reaction are the Cope and Claisen reactions. The second type of pericyclic reaction is an electrocyclic reaction, which we see in number 2. And the third type should be really familiar because we just did it. It's Diels-Alder, and it's considered a cycloaddition. I want you to take away two things from pericyclic reactions. Is one, they go through a concerted mechanism, and two, they have cyclic transition states. Now, this cyclic transition state in the concerted reaction mechanism is important to stereochemistry. Because of that concerted reaction, they occur with a retention of stereochemistry. And so we can show this in the example below, in which we're using 1,3-butadiene with fumaric and maleic acid. These are just isomers of one another. So in fumaric acid, the acid groups are on opposite sides, which makes it the E isomer, or you can think of it as trans. And in maleic acid, the acid groups are on the same side, that is the Z isomer, or cis. Now, if we think about how to arrow push for the Diels-Alder reaction here, we're going to end up with our alkene being here on the ring. So let's go ahead and draw our two products. Now, in fumaric acid, they're on opposite sides, or like we said, trans. So that means they will be trans in the product. Whereas in maleic acid, they're on the same side, or cis, which means they will be cis in the product. Now, that's a fairly simple example. What happens when you have a cyclic starting material? Well, then you have to take into account endo versus exo transition states. And so below we have the reaction of 1,3-cyclopentadiene with maleic acid. In the first top transition state, the diene is approaching from the top and your acid groups are on the outside, or I like to think of them as they're exiting, so that is your exo product, or in this case your exo transition state, which will give you your exo product. Whereas on the bottom, your acid groups are up under the diene, they're facing in, that is your endo transition state, which will give you your endo product. Now, these produce bicyclic rings that only differ in stereochemistry. Now, something to note here is that depending on starting materials, temperature, the reaction in general, there will be preferences for endo versus exo, and that is something we're going to be looking at in today's lab. We're going to look at the preference based off temperature. And when you think about temperature, you then have to take into account kinetic versus thermodynamic products. So if you will recall, the kinetic product forms the quickest, and it occurs through the lowest energy pathway. The thermodynamic product tends to prefer higher temperatures, and it has access to all energetic pathways. Now, the reaction we're going to be looking at is the reaction of furan, seen here on the left, and N-phenylmelamine. Which will give us an endo and an exo product. Just in this case, we're using two cyclic starting materials. So here, where the N-phenyl is facing out, it's exiting, is our exo product. And then when the N-phenyl is kind of facing up under, that is our endo product. There are three main questions we want to answer in today's lab, and that is the entire goal of this lab, is to answer these questions. The first being, what product is thermodynamically favored? The second being, what product is kinetically favored? And then the third is, can the endo and exo products be interchanged? Or more simply put, is this reaction reversible? We will have to do a two-step synthetic route to get to N-phenylmelamine and to make our Diels-Alder product. So we will make our N-phenylmelamine from the reaction of maleic anhydride and aniline. Once we get to the N-phenylmelamine, we can then do the second step here on the bottom. That was the first step. This is the second step, which is our Diels-Alder reaction to give us our exo and endo products. However, the synthetic route this week is not the most in-depth part of the lab. In fact, it's going to be the product analysis. And we'll be doing two different types of analyses this week. The first being TLC, or thin layer chromatography. And what we will be looking at is the RF values of three distinct compounds. Now, looking at the RF values in 1:1 ethyl acetate hexanes as our eluent, we have N-phenylmelamine, our starting material, which is here on top, with an RF of 0.68. In the middle, we have our endo product at 0.47. And then at the bottom, we have our exo at 0.33. And how this will be useful is you can spot against the standard N-phenylmelamine your product that you isolate. And you'll be able to see, A, did your reaction go to completion? Do you have any remaining starting material? And then you can check for the presence of one or even maybe two products. The second analysis we will be doing is proton NMR. And at this point, you need to recall the N+1 splitting rule. So if you have a proton surrounded by two other protons, you'll do 2 + 1, which will give you 3, and that'll be a triplet. Or if you have a proton next to another proton, that'll be 1 + 1, which will give you a doublet. And so let's use that as an example. So let's quickly sketch a doublet. What's even more important to this lab is the distance between these two peaks, which we're going to label as J. We're going to consider the two protons we're looking at as A and B. And this distance is called a coupling constant, which is measured in Hertz. We want to examine these coupling constants in our endo and exo products. But first, let's look at a more simple example using the isomers of bromopropene. Here on the left, you have the E isomer, or the trans, where your bromo and your methyl group are on opposite sides. On the right, you have the Z isomer, with your methyl and your bromide on the same side. What you need to notice, however, is the differences in their coupling constant values. The E isomer has a much larger coupling constant, and this has everything to do with the dihedral angle. So in the E isomer, you have a dihedral angle of 180 degrees, whereas in the Z isomer, the angle is 0. So we can make a generalized statement here that the E, or trans isomers, have greater coupling constants than that of the Z cis isomers. And we get this generalization from the Car+ relationship, which examines the s orbitals of your protons. So looking at it for the 180 orbital overlap, you can see pretty decent overlap of your two different s orbitals. Whereas at the 0 degree, that overlap is not quite as good, so giving it a lesser Hertz value or coupling constant. Whereas in 90, there's no overlap, just some intersection at the node, so you hardly get any coupling constant at all. You can then examine your gray area on the Karplus relationship graph here, which will give you, by looking at your dihedral angle and your Hertz values, will give you around about the amount of coupling you should expect to see for a certain dihedral angle. To help you out, I've already modeled your endo and exo products of the reaction you'll be using today. And what you will see is that for your endo product, that dihedral angle of your two bridgehead protons is at about 38 degrees. Whereas in your exo product, it's at about 80. And so at this point, I've helped you as much as I'm willing to today, and I want you to figure out what your expected coupling constants you think they'll be, and then see what they end up being in your own personal proton NMRs. This will be a 2-week lab, in which week 1 you will be synthesizing your products and setting up your Diels-Alder reaction. You will then be split into 3 groups for 3 different temperatures: 0, room temperature, and then 0 to 60 right before lab the second week. The week 2 will be dedicated to just working up your Diels-Alder reaction and then product analysis. Good luck, everyone. I hope you have fun with the Diels-Alder reaction.